Morning guys, and welcome to part 2 of the worked exam answer video that I shared part 1 for yesterday. So we're going to be having a look at another catalysis question, and this time we're going to be having a look at the auto catalysis example where we have potassium manganate reacting with sodium ethane dioate in aqueous solution. So in terms of this example, I do think it's a bit more complicated, although we haven't been asked to write the equations that show how the autocatalyst works in this particular example. Those equations you do need to be aware of, and akin to the previous catalysis video that I did with the peroxide disulfate and the iodide ions with Fe2+ ions as the catalyst, those two equations can be worked out by writing redox equations kind of for each of the steps. So again, it's how much you want to learn versus how much you want to kind of back yourself to be able to work out on the day. Now in this particular question, we are still having to write an equation for the overall redox reaction, which is still going to involve writing half equations and then combining them together to get the overall equation. And again, that is definitely what I would do as opposed to learning this equation off by heart. We have to identify the species that then acts as the catalyst, which again is meaning we're going to need to be aware of what autocatalysis means, because that's going to tell us what the catalyst is going to be. And then it's explaining why this species can act as a catalyst in terms of its properties. So essentially, why does it work as a catalyst? Okay. Part 2 is then a question that I've seen a couple of times, whereby you've got to sketch a graph to show how the concentration of one of the reactant ions, which in this case is our manganate ions, varies with time in the reaction. And then we have to explain the shape of the graph that we draw. Now, for this, it's getting you to think about, again, the fact that it's autocatalyzed. Think about what that means in terms of when the reaction is going to be slow, when it's going to speed up, when it's going to stop, etc, etc. Now it is only a sketch, so we don't need to be thinking about, plotting exact points, but it does need to have the right kind of shape, okay? And then we're going to have to explain it, which I will of course do. So starting off with the redox reaction, as I said, I wouldn't be learning off by heart this equation, but what we do need to know is what happens to the manganate ions and what happens to the ethane dioate ions within this redox reaction. So the manganate ions are going to be reduced to Mn2+ ions. And so long as you know that, you can then construct the half equation, as I'm about to do. And so long as you know that the ethane dioate ions are oxidized to CO2, then again you can construct that half equation and then just use your redox skills to join those half equations together, which is exactly what I'm going to show you now. So the bits that we need to know, as I've said, is that we're going MnO4- to Mn2+ for our reduction half equation, and that we are going from C2O42- to CO2 for our oxidation half equation. So those are the bits to know. Then we can fill in the rest of the equations as we would any half equations. So for the top one, the manganese atoms are balanced. To balance the oxygen, we're going to add 4 molecules of water on the right hand side, which then brings in some hydrogen that we need to balance, which we're going to balance by adding H+ ions. And then we've got to balance our charges. So right hand side +2, left hand side +7, +7, +2. Need to bring the charge on the left hand side down, doing that by adding 5 electrons. Now I suspect that you will come to learn that off by heart. I know it off by heart. You will if you practice writing it out enough, but it's also important we know how to work it out as a skill. For the ethane dioate one, which is perhaps less commonly used, the first thing we have to remember is we've got to balance the carbon atoms. So we're going to have to do 2 CO2, and that can be forgotten. Now, the benefit of remembering that is A, you've got the right number of carbons, but you've also now balanced out your oxygens as well. So the only other thing we then need to do is balance the charges by adding 2 electrons here. Now, in terms of combining these together, it's not the nicest example because we've got 5 electrons being gained and 2 being lost, but we can multiply the top equation, everything in it, by 2, and for the bottom equation, multiply everything in it by 5, and then the electrons will cancel, and then I can join those together. So my redox equation is going to be 2 MnO4- plus 16 H pluses, not going to include the 10 electrons because they'll cancel, plus 5 C2O42-, and that is going to make 2 Mn2 plus 8 H2O plus 10 electrons I'm not going to write because they'll cancel, and 10 CO2. So that's your redox equation. Now, some people may just rote learn that. Personally, I don't think that's a good use of your memory, but I'll leave that up to you. Identify the species that acts as the catalyst. So when we think about autocatalysis, the reaction is catalyzed by one of the products. So the autocatalyst in this reaction is the Mn2+ ions. They are our catalyst. Now, if we think about some of the stuff we've already talked about in these recent videos, it's a transition metal. So it exists in variable oxidation states, and it's going to change from +2 to +3 as the temporary oxidation state, and then turn back into +2. It's positive, and these 2 ions that are trying to react with each other are negatively charged. So we're going to get repulsion, and there's going to be a very high activation energy. Whereas if we have a positive Mn2+ ion, it can pick off the first negative ion. There would be an attraction rather than a repulsion. Make our Mn3+ ions, they would then pick off the second negative ion and reform our Mn2+. So that is our catalyst, and that everything I've just said there is explaining how the properties of the species enable it to act as a catalyst. So it's a transition metal, so it has variable oxidation states. And as I said, in those 2 equations that we're not asked for here, but we could be, it would be that the Mn would go from Mn2+ to Mn3+, and that would then be our temporary intermediate version, and then obviously it would be reformed as Mn2+. The other key part is that it's positively charged, so the Mn2+ ions lower the high activation energy that exists because 2 negative ions are reacting together, and these will repel. And it will lower the high activation energy because it's positively charged. And so then it would be a positively charged ion attracting a negatively charged ion. And that's exactly the same for why iron was used in the peroxodisulfate and iodide ion reaction. Again, we had two negative ions repelling, high activation energy. When we add Fe2 plus to that reaction, it's got variable oxidation states. Fe2 plus becomes Fe3 plus and goes back to Fe2 plus. And again, because the iron ions are positive, then that brings the very high activation energy down as well. Exactly the same reasoning. Okay. Now, let's sketch a graph. So we're thinking about how the concentration of the MnO4 minus varies with time. So on my axes, what is changing? So our independent variable is time. So that needs to go on the x-axis. We don't need to make an assumption about units, although probably seconds. And then the y-axis is the thing that we're measuring, which in this case is the concentration of the MnO4 minus ions, which I can use the square brackets like that to show that that's the concentration of that, which would then be in mole per decimeter cubed. Again, I guess the units are not the important part. Now, because the product is the catalyst, there isn't any catalyst at the beginning, because only when we have made this Mn2 plus can it then react with the MnO4 minus ions to make Mn3 plus, for that to then react with our ethane dioate ions. So initially we're just stuck with this high activation energy because of the repulsion between the negatively charged ions. So, and I'm going to do this in pencil first, initially the concentration of the MnO4 minus is going to be pretty high because it's a reactant. Again, it's all relative, but I don't want to start it down here on my y-axis, somewhere towards the top. And initially it's not going to decrease very quickly at all, because we've got that high activation energy and repulsion between the negative ions. However, when we start to make some of the Mn2 plus, which is our catalyst, the reaction is then going to speed up and do so pretty quickly. It's not going to be kind of a slow and steady increase in the rate of reaction. As soon as we've made Mn2 plus, it can start attacking the MnO4 minus and reacting with that, generating the intermediate to react with the ethane dioate ions. So the reaction is going to speed up significantly, which means that the concentration of the MnO4 minus is going to decrease a lot more rapidly over time, and then eventually you won't have any of it left. So the reaction will peter out to nothing. So it's kind of like an inverted S shape. And in terms of explaining the shape of the graph, I would argue there's kind of 3 points on the graph that we're going to want to be explaining. The first part being initially, when the reaction is very slow. The second part being referencing the formation of the catalyst, which is going to then speed up the reaction. And then part 3, all of the MnO4 minus is used up. So obviously the reaction is going to come to a halt. And those are the 3 things that we're going to need to explain. So, part 1. The initial reaction is very slow, high activation energy to negative ions reacting and repelling. So change in the MnO4 minus concentration is slow and insignificant. Step 2, the Mn2 plus autocatalyst is produced, and so the reaction speeds up. Meaning the concentration of the MnO4- decreases much more quickly. And then step 3, all of the MnO4- is used up. And so the reaction ends. And there you have it. So for 4 marks, you're going to get 1 for the shape of your curve, sort of that inverted S shape, and then you're going to get a mark for each of those 3 points that you've then explained on your sketch. And that is the autocatalysis example. Now, with the exception of writing out the 2 equations that show how it catalyzes the reaction, that's pretty much what they're going to ask you about this example. So hopefully that's all been fairly clear. They might ask you to define autocatalyst, which is when one of the products of the reaction is then the catalyst for that reaction. And other than that, that should have you covered. But if anyone has any questions or anyone's seen any other sort of things that they've been asked to do, please don't hesitate to get in touch. Otherwise, thank you so much for watching, guys. I hope you're all well, and I will catch up with you again very soon. Thank you.